This topic is on current and the types of materials that can carry current. So current's pretty simple. If I take a charge, let's make it a plus charge, and I move it, I've got current. Current is charge in motion. And I can basically define it by the letter I. I is typical for the symbol in current. And that's going to be equal to the change in the amount of charge, Q being the charge, divided by time. That might look a lot like velocity. Velocity is defined as change in position over change in time, which is given in units of meters per second. Current looks almost the same way, only it's coulombs per second. And we know that that is now defined as an amp. For Ampere, one of the early scientists. I don't remember his first name. So, amp is usually just given by the letter A. And of course, you use it as milliamps, often being 10 to the minus third amps. Now, that's really all there is in current. But we could start talking about where current's moving. So that kind of switches us to materials. So let's try conductors. An example, copper or aluminum. Both of those are excellent conductors, and you'll see houses and so forth wired in copper, and you'll see them sometimes wired in aluminum. Sometimes the industrial facilities are wired with aluminum. So they're good conductors. They let charge flow easily. So in the picture that we have, if you have a wire of copper, for example, then the charges that are free to move are the electrons. So it's the negative charge, if you will, that is free to move. The positive charge is in the nucleus. Those aren't moving in the conductor. But if I get that charge to move, that's current. Now typically, this is actual, but by convention, we think of current a little bit different, and that is we think of a wire and we think of positive charges moving, and this is what we call positive current. Even though the positive charges don't really move, we generally do most of the problems as if the positive charge moves. Sometimes very reputable books will do it the other way, and some books use, and they'll state it right on the front of the book, electron flow. Oops. So it's not impossible to see that some electricians follow the convention of electron flow and some don't. But in this case, if you have a wire, the current being given conventionally as positive in that direction is really made up of electron flow going backwards. So you'll see it both ways, but at least physicists and generally electrical engineers, but generally by convention, that's the way we think of current. We think of it as the direction that the positive charge is flowing. Now, that's pretty easy. Copper, aluminum, they have extra electrons. Those electrons flow. They flow easily. There is some resistance. We'll talk about resistance later, but that's conductors. Now let's go to the next one. Again, we're talking about materials. In this case, we're going to talk about insulators. An example, maybe glass, rubber, things that we typically think of that don't let charge flow. So it's just that. Current equals zero, effectively. So it's an insulator. That leads us to the last material. And that one's kind of special. And again, it's a material. And that would be semiconductors. You might say, well, why do we need to know semiconductors? Well, it turns out that as we look at the circuits that run the X-ray tube, they have semiconductors in the circuit. They play a prominent role, and we want to describe those elements of our circuit as our first circuit element. Semiconductors have just the opposite story that Max Planck had when he got a Nobel Prize for um, finding energy of a photon. In this case, there was a Nobel Prize given, but it was around the 1940s for the discovery of semiconductors, and it's because what they did was truly brilliant. They were invented, literally. They didn't exist in nature. This was invented. So here's the basic story, and I'm not going into a lot of it, just a little bit. Basically, what we'll take is we'll take an insulator, and the example that we had from before was glass. Well, glass is mostly silicon. So we'll take silicon glass in here, and basically what will happen is we will put silicon in here, and they bond together, and these dots represents the bonds that each silicon atom shares with its neighbor. Now I put one in here that didn't have anything, and that's because the trick in semiconductors is they take this insulator and they dope it. They put an imposter in the silicon bond structure so that there's an atom in there that is not supposed to be there, but it turns out quantum mechanically it fits. So now we're going to do something that is, well, brilliant. Instead of putting another silicon atom in there, I dope this insulator. And I dope it with the next element up in the periodic table, and that's phosphorus. Phosphorus jumps in, it's got plenty of electrons. In fact, it's got one too many. So I could write it here as there's an electron that has nothing to do. All the electrons in there are busy with this silicon structure of the silicon crystal. They're busy, but because it's an imposter, because it's phosphorus, it's got an extra electron. We call this N-type because extra electron carries current. I'll roll my page. Now, by itself, we've made a poor conductor. Aluminum and copper are a lot better, so we've done nothing so far. We'll do this trick again. We'll make another semiconductor, and we'll put the silicon in there as we did before. And this time, instead of putting phosphorus in there, we're going to go down one element in the periodic table, and that's aluminum. Now, aluminum has one less electron than it needs. So it jumps in, it's pretty close. These dots kind of represent the bonds that the electrons form. So it goes ahead and it forms the bonds with aluminum, but it's missing one. And so for all intents and purposes, it acts like it needs an electron. Since it needs an electron, we think of basically a positive charge wanting to fall into what we will call a hole. This is a p-type, and it has extra plus charge. So we get the electron to move, and by falling into holes, and it appears plus charge moves. Again, we've created a bad conductor instead of, I guess I should make this guy blue. We created a bad conductor. Copper and aluminum do better. But now the real magic comes. If I put a P-type and an N-type semiconductor together, that's the Nobel Prize. So what happens is I go ahead, redraw my two semiconductors, and I paste them together. So I have the P-type on one side, and I have the N-type on the other side. I'm sorry, I reversed those. Let me fix that. This is going to be the N-type and P-type. Now, since there's electrons available in the N-type, they tend to fall into the P-type. So here's these electrons. I'm just going to switch to the normal color. So here's these electrons. They fall into the holes. And the effect is they keep falling into the holes, and what they do is they leave behind positive charge. So as they fall into the holes, what was a neutral material with the equal number of electrons and protons now has too many electrons. And what's left behind in the N-type is too many positive charges. So they were happy until you put those two things together, and then all of a sudden they built up a bunch of positive and negative charge on each other. And this region right here is known as a depletion region. So what does the depletion region mean? It means no charge carriers. So the current can't go through the depletion region. We literally have a no-go zone. So if you like, or if I shade it a little bit, this whole region in here is no-go. It doesn't have any charge carriers. So the N-type acts like a conductor, maybe not a great one, but it's a conductor, and the P-type acts like a conductor, but the depletion region, because they've been put together, does not transmit current. Now, what do we do with this amazing thing that got a Nobel Prize? Well, it turns out that if you hook this PN junction, I should have drawn it black. If you hook this up to a circuit, you can put an electric field in there by creating a voltage in the wires. If that electric field, first of all, I'm going to go up here and just outline what the electric field looks like in the depletion region. It goes from positive to negative charges. That's the E field. Now down here, in this situation down here, I'll draw that depletion region. Plus, 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 minus, 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 minus. And we now know that there's naturally an E field. E, we'll just call it natural. That natural E field now is the thing that's creating the block, not letting current flow through. If we try to push current in this direction, what will happen is we will create a special E field I'll say it's induced. That E field's induced when that current's going in that direction. So what the two E fields will do is they'll add up, and these two E fields will cancel. And suddenly, what we have is the current can go in that direction. Now, if I do it the other way around, I'm going to draw another PN junction. I'm going to try to put current in the other direction. Here's my original depletion region. And now here's the E field that had been set up because of that depletion region. Now, what's happened is the E field that I'm trying to put in with this induced current, oops, there's the induced current trying to go in. Well, that's the wrong way. Sorry. E field's add. So, current is blocked. So what's happened is we have made what we call a diode. And a diode, which becomes the building block to transistors and the building block of all those things that we use in our everyday lives, the diode is the thing that got the Nobel Prize. They literally tricked Mother Nature and sent in, created what is effectively a check valve. That is, it lets current go one way, but it doesn't let it go backwards. The circuit element for this, and it's the first circuit element we have, looks like that. And in that case, what it means is it's like an arrow. It looks like an arrow with a block here. And what it means, quite literally, is I's okay in this direction, and I is blocked in the other direction. So it becomes like a switch. We will see diodes in use in the X-ray tube. It's an essential part of the circuit that creates X-rays. Thanks for listening.